Hello students, welcome back. The final section of this notebook, Cauchy-Schwarz inequality, is an optional topic, at least for now. In chapter 6 of our textbook, I think it's chapter 6, let me check. Let's go to table of contents. Is it chapter 6? Yes, it is chapter 6. Chapter 6, scalar products and orthogonality. In chapter 6, we're going to study scalar product in more abstract point of view. That's where we're going to come back and cover the Cauchy-Schwarz inequality in detail. For now, it's an optional topic, in case there are some students who are interested in it and also capable. This is what we are talking about. The scalar product is always less than or equal to the product of the norms. Also, the inequality is the general case, but the equality holds if and only if two vectors are parallel. Now, if we take the classical point of view, that is, in planar geometry, in pre-calculus, what did we do? We defined the dot product like this. Magnitude times cosine of theta. In this case, this cosine of theta is always less than 1, less than or equal to 1 at very most. Therefore, this is always less than or equal to the product of norm, because we just replace cosine of theta by 1. There's a bit of a problem though. If we don't have the concept of angle, what if we have infinite dimensional space, for example? If we don't have angle, then this idea breaks down. Even if we have n-dimensional space, it's gonna be a little bit difficult to get appropriate plane and then define appropriate measurement for the angle. So this method is not very good. So how do we handle this? This is the proof that our textbook author uses. Let's begin with the orthogonal component. Okay, let's begin with the orthogonal component. And this is vector x, that's vector y. And then we're going to decompose blue vector x, into the parallel and orthogonal component. Parallel component using the let me increase the font, excuse me. Using the parallel component formula, you're going to get x dot y over y dot y times y. That's this green. And then this one. This one is the orthogonal component is just x minus of that. Diagonal minus this, so that we get the vertical component, perpendicular component. So this is orthogonal component, and then that's the parallel component. All right. From here, let's apply the Pythagorean theorem. Okay, all right. So the diagonal is x, so diagonal squared, or hypotenuse squared, is equal to green squared, and then brown squared, this one. Okay, that's the same as this one, but if you put over here, then you're gonna get Pythagorean triangle, or you can move this green over here on top. In any case, you're gonna get a triangle, so you can have Pythagorean expression. Hypotenuse squared is, well, adjacent squared plus opposite squared, basically. Okay, all right. And then we're going to apply some algebra. We can take this one outside of this norm, and by the absolute homogeneity property, we can take it out. We don't need absolute value because this is going to be squared anyway. And then we do something ingenious here. Drop this part. So replace this by 0. Consequently, the third line is got smaller. The third line is smaller than or equal to the second line because this positive or non-negative drop down to 0. Let's go over here. The brown is the orthogonal component and we are disregarding it. And of course, we're going to have equality if there's no brown to begin with. In that case, and this blue and green or blue and red are parallel. In that case, there's no brown to begin with. In that case, we have 0. Otherwise, this is strictly greater. Alright, now what do we have? This is x dot y squared, so that's what goes to the numerator here. And down here, y dot y and then square again. That's norm of y to the fourth power. You see, y dot y is already second power. Square again, we have fourth power. So we have cancellation. Fourth power down here, second power up here. So second power down there. We're almost there. Now flip this denominator to the other side. Then this is what we're going to get. This one flipped over there. We got that. And what do you get? We get norm square times norm square is greater than or equal to scalar product squared. All we have to do now is to take the square root of both sides. Norm times norm is greater than or equal to the absolute value of this dot product. And that is the desired inequality. Cauchy-Schwarz inequality. Let's see. Font is too big, so I cannot put everything in the same viewing window. So this is what we wanted. Alright. And then we take parallel and orthogonal components, green and brown, and use Pythagorean rule. Hypotenuse is blue, so the original vector x. Blue squared is brown squared plus green squared. And then apply some algebra. Absolute homogeneity, and then we can take this one out. And then just completely throw away this part so that we reduce. So we have inequality, not the equality anymore. And then some further algebra. Denominator becomes absolute value, fourth power, and then after simplification we have norm squared in denominator. Flip to the other side, we get what we want. Okay, that's how our textbook author proved it. Tough fact to follow. In case you have a little bit of difficulty following all this, I prepared an alternative proof. You may prefer it or maybe you wouldn't. I don't know. Let's begin with an expression like this. F of t as t vector x minus vector y dot t vector x minus vector y. Basically this is dot product of itself. So this is always greater than or equal to 0. It's always greater than or equal to 0. Now quadratic expression always greater than or equal to 0. That means we should not have any real root because if it has a 0 then it has a root. So b squared minus 4ac has to be less than 0. The worst possible case is being equal to 0, so we have equality. By the way, this expression can be rewritten as this kind of foiling. And this one is quadratic expression. So at squared minus bt plus c form. And you can use that b squared minus 4ac. b squared minus 4ac is less than or equal to 0, so that we have either no solution or at most just one solution. And then just some algebra. Divide everything by 4 and then you're going to get what you want. This is nothing more than norm squared. Norm squared. Divide by 4 and then take square root. We get Cauchy-Schwarz inequality. Now, when do we have equality here? Well, one way to see it is going back to this discriminant, and b squared minus 4ac is equal to 0. In that case, let's see. No, that's not really helping. We'll have to go over here, and that's becoming equal to 0, which means tx minus y is equal to 0. In other words, y equals to tx. So x and y are parallel. So tx minus y is 0, or y is tx. We have parallel vector. That's another proof. Which one do we prefer? The textbook's method depends upon picture and then orthogonal and parallel component. And then Pythagorean theorem. Works out great. If you're not really into orthogonal component, proof 2, then you can use quadratic expression and then you can use discriminant. You don't have to rely upon any kind of picture. That could be either advantage or disadvantage. Anyway, we just went through Cauchy-Schwarz inequality. Okay, we did that, so let's go to the next concept. Angle between two vectors. Because of Cauchy-Schwarz inequality, we can define an angle like this. This quantity is between -1 and +1, because from here, divide this by the right-hand side, then we get this fraction, and that's less than 1 in absolute value, so this quantity has to be between 1 and -1. As a matter of fact, this quantity here should not be absolute value anymore. Okay, absolute value is less than or equal to 1, so through the absolute value, then we have this quantity is between -1 and +1. And therefore, we can define cosine of theta like that, or theta as inverse cosine of this quantity. So that's how we define angle. And we can do that even when we don't have picture. Sometimes we have infinite dimensional vector space. In that case, we cannot draw any picture. Graphical method does not make any kind of sense. In that case, can we just throw away the concept of the angle? Well, turns out you don't really have to. You can always define your angle using inverse cosine function because of Cauchy-Schwarz inequality. Okay, now that we have angles, you can go back and prove triangle inequality or subadditivity. Same thing we have done before. And then fold it out there, and then this is less than or equal to that because of Cauchy-Schwarz inequality. And the right hand side is complete square, and then we have what we want. This one squared is less than that one squared, so taking the square root of both sides, we get what we want. Distant function, this is an important concept in analysis. d of xy is called a distant function if it satisfies number 1, symmetry. dxy is equal to dyx. Distance from x to y is the same as distance from y to x. And then positive definiteness, distance is always greater than or equal to 0. Moreover, distance is 0, means we have the same points. And finally, the triangle inequality. Distance from x to y plus y to z is greater than or equal to distance from x to z directly. So turning around takes more than going straight ahead. Form a sort of triangle. Do we have a picture here? No, not really. Anyway, if we have that kind of thing, then we can call it a distant function. And any set with distant function is called a metric space. And Cauchy-Schwarz inequality actually proved that any kind of vector space with a norm is a metric space, and we can do all kind of analysis there as well. Analysis, I mean by study of functions like limits and convergence, sequence and series, and things like those. With a little bit further adjustment, you can even do differentiation and integration. Anyway, all those can be done based upon Cauchy-Schwarz inequality. All right, I went a bit too much about all those advanced mathematics, but it's okay. This is optional lesson anyway.